today's topic. And again, we will be building more upon what we discussed last time in the linear regression, right? I wanted to check with you and see if anybody has any questions or any thoughts or anything which I can help you get more clarity on. Feel free to ask that. Good evening, Abhijit. So last time, can anybody tell the class what we did in the last class? I will unmute you, so just raise your hand. Whoever wants to summarize very quickly so that everybody is on the same page. Why should we use a model? Hari says yes. Okay. So Hari, maybe I will unmute you. So if you can just speak up on the microphone and let everybody know what we did and a quick summary of that. Yeah.
Yeah,
Hari. Yeah. Go ahead.
yeah. See, last time we had this thing about the regression part. So the t value, f value, and based on
Yes.
that, you computed the having a multivariant with MPG having a base and
Sure.
cylinders and other things.
Sure.
So I also sent you a sheet about what would be the model for that. This thing model I mean is the regression.
Uh-huh. Yeah. Okay. And any other things that you want to highlight? So, what were the key learnings that we did, or any other thing that we should think
The
about?
key learnings is like we had that graph of the line of this thing. I mean, to the have the I couldn't get that line. What is that line? We call it as the linear line.
Mm-hmm.
So based on that, we can easily find out where is the outliner and those things. This is what
Okay.
the fact.
Okay. Okay. Thank you, Hari.
Yeah.
Anybody else wants to take a stab? Anything else? I mean, so what is the algorithm that we use for fitting a linear line or linear regression model? If you can come on the phone and talk about that. Don't be shy. I mean, don't be shy of making mistakes as well. So raise your hand. I will unmute you. So maybe let's see who can do. Gaurav, maybe you want to talk? What is the algorithm that we use for fitting the line? Yeah? Shall I unmute you, Gaurav? Okay, so give me a moment. So Gaurav, you should be unmuted now. So let me know what you think.
Okay, so what we started off is we have a independent variables and we have one dependent variable. So in our
Mm-hmm.
case, it was MPG, and
Yeah.
dependent variables were cylinders, number of cylinders, engine displacement,
So sorry,
torque.
sorry, sorry, Gaurav. Before you move on, so can you just, for the benefit of the class, can you just explain what is independent variable or what are independent variables and what is a
So
dependent variable?
So a dependent variable is a variable which is dependent on independent variables. For example, if I want to calculate the price of laptops, for example, this year, so
Uh-huh.
that price will be my dependent variable, and the factors which will impact this price will be my independent variables. So, for
Right,
example,
right,
it can be a new model, new technology, or something like that.
right, right. Okay. So explanatory variables, basically variables which are explaining things for your dependent variables, they are called independent variables, and the one that you're trying to explain or predict, that is the dependent variable, right?
Dependent. Exactly.
Okay, okay, good. Move on. Yeah.
So after that, we learned about before doing a regression, we'll try to find out correlation between the independent variables so that there is no point of collinearity. Or,
Mm-hmm.
then we run a regression model uh,
Yeah.
through through Excel, and
Yeah.
then we try to find out t value and f value. If the value of t is greater than 2 and less than minus 2, then it is significant. Or in the case of f value, it should be less than, no, it should be greater than 0.05, then it
Sure.
is significant.
Sure.
Am I right?
Right. Right. Okay.
Uh,
Great. And
so
yeah, go ahead, Gaurav.
So this will determine the quality of our dependent independent variables, and henceforth we'll use these variables. So, for example, there are five independent variables, and out
Mm-hmm.
of those five we got three. So we'll put them in the equation of y is equal to constant plus x1 plus x1 into c1 plus x2 into c2 plus x3 into something like this.
Yep. Okay. Thank you.
And then,
Okay.
okay, thank you.
Thanks, Gaurav. Okay, so now who can tell me what is the algorithm that we use? What is the technical name of the algorithm that is used for fitting the model? Ambuj, you want to try? Shall I unmute you? Okay. Ambuj doesn't want to talk about that topic at this time. Okay, sure. So you can watch the video, Ambuj, not a problem. How about Nida? Can you tell me what is the name of the algorithm that is used for fitting the line? Okay.
Uh,
Go ahead, Nida.
is it that we are looking for the best fit line?
Yes.
Yeah, first of all, we check for the correlation,
Uh-huh.
and if there is, I can explain from the beginning like what we did. First,
Sure.
we did simple linear regression. In
Uh-huh.
that, we looked for the relation between our dependent variable MPG, and we had the independent variable weight.
Mm-hmm.
So after checking the correlation between them, we went for the linear regression model, and we had the equation y-intercept, it's equal to beta naught plus beta 1 x.
Yeah.
So beta naught and beta 1 were the coefficients,
Mm-hmm.
and x was our independent variable.
Okay.
I think it was weight.
Mm-hmm.
And
Okay.
then after checking the correlation between them, we did the linear regression model, simple linear regression model. Then we
Right.
went for multiple linear regression model.
Mm-hmm.
There we checked for like R square, S stats, T stats, and F value. That's F value should be less than 0.05, and
Mm-hmm.
T should be between mod 2, less than or greater than mod 2.
Yeah.
And then
Yeah. Yeah. Greater than
we
mod 2.
looked for the
Mm-hmm.
we checked whether our independent variables, they are significant or not,
Yeah.
and any based on the values of p value and t value.
Yeah.
And then we eliminated the not significant variables.
Yeah. That's great.
And yeah, after that, again with the significant variables and with our MPG, that's the dependent variable, we done the correlation.
Mm-hmm. Yeah.
And that was our like
The final
y-intercept.
model.
Yeah, y-intercept is equal to beta naught plus beta 1 x plus
Yeah.
beta I think beta 2 x2.
X2. Yeah.
Yeah,
Yeah. Yeah. That's great. Okay. Thank you, Nida. Thank
thank
you so
you.
much. Yeah. Okay, now let me ask who can build the linear regression model in Excel. I mean, so the task data that we have, who can do it for the class so that we can just quickly revise, and then I will jump on into R, how to build a model in R, how to interpret the model in R, and then we will also do in SAS, right? So today we might wrap up a bit early and we may skip the break because it can be wrapped up earlier, right? But I want one volunteer to build this model in Excel for me. Who wants to do it? So I will give you the control and we will look at your screen. Anybody who hasn't tried yet should raise the hand, or anybody who wants to try it on their side. Nida says I can do it. So okay, Nida, let me make you the presenter. Give me a second. Thank you, Nida, for volunteering. I have made you the presenter, Nida, so if you can share your desktop. And I will unmute you also, so you can just sort of like give the class a quick view of what you're doing. Let me just unmute you. Give me a second. Okay. You are unmuted, Nida, so you can speak up.
RP, where from shall I start? Shall I
So
start with the
yeah, from the Excel file that you have, if you can just begin that with that Excel file and then go to the data analytics tool pack and build the linear regression model.
with the multiple independent variables?
Multiple, yeah, multiple, yeah.
Yeah, sure. Please give me a minute. I want to just.
Sure. So folks who joined a bit late, first of all, welcome. We just did a quick revision of what we covered last time, and Nida has graciously volunteered to walk us through the building the model again in Excel. So we'll spend maybe 5 minutes just talking about that, and then we will jump into R. We will build the model there, and we will also do the same thing in SAS, and then we'll try to interpret, right? Before we go there, we'll talk about two very important concepts which are pending from last time, which is the multicollinearity and heteroscedasticity, right?
RP, is this the one that I need to download? I'm not sure because I'm only getting MPG predicted over there.
No, the actual raw data. So if you go back to the actual cars data where you have the MPG and all the predictor variables, this data is there actually in today's learners folder as well. So if you go to today's learners folder, I mean, or maybe actually go to the previous one. I think it should be there. That would be better. The one on 27th August, Nida. Yeah.
Pardon me, my computer has gone, my laptop has gone very slow.
No problem. I understand. So take your time. Not a problem at all. Even this one has the, oh yeah, this is good. So you can build on this one. So take actual miles per gallon as the dependent and take the column C, D, E, and F and G as your independent variables.
Okay. So first of all, I'll go to the data analysis tool pack.
Yeah, so everybody is able to see Nida's desktop. Can you just quickly confirm? Yes, no? Yeah, okay, good. Yeah, please continue, Nida.
Starting with the regression, I'll take the input data. That's my actual miles per gallon.
Yep.
And then I will go to my input X range. I'll select my cylinder, engine displacement, horsepower, weight, and accelerate.
Right.
Oh, sorry, just give me a moment.
Sure.
And then I will check on the levels. My confidence level is 95%.
Right.
And then I will check on the residuals and okay. Oh, should be D.
No, actually, you are right there, Nida. That is right. So make it C again. Yeah, this one is C. That's fine. The upper one is B. So starting with B1 to whatever that thing is, B393, I think. It shouldn't be G. Yeah? Yeah. Now you should be good.
Okay.
There you go, right?
Here is my output here. First of all, I'll check for the R square value.
Can you zoom in a little bit so that everybody can see it? Just a little bit. And then expand the columns also. Yeah. Okay. Yeah. Yeah. That's fine. That's fine. That's good enough. Yeah. Okay. Yeah. You were saying first you'll check the R square value.
Yeah, R square value, it's quite high. So it means like there is a correlation, and then I'll check for the adjusted R square. So like anything above 20 should be good since we have 70 here. So that means there is a strong correlation. Then I will go for my significance f, which is my p-value. It
Right.
should be 0.05, less than 0.05. So
Yeah.
here it's 9.8 e raised to power minus 101. So I think it's like much less than 0.05. And then I will check for my f value. F value should be more. I don't actually have a
Yeah.
range, but
Yeah.
higher it is, the
There
better
is
it
no
is for
magic
us.
cutoff. Yes. Yeah. So
Yeah,
just stop for a minute, Nida. I just want to explain because somebody had a question earlier on.
yeah, sure.
So the what is the F statistics testing here? Can anybody tell me the answer of that? What is the F statistics and what is it that we are testing in column E and F? What is the null hypothesis here?
Uh,
Who can tell me?
shall I go ahead? What's it?
Yeah, sure. You can
Null
try.
hypothesis is that rate is MPG is none of our other independent variables
Yes.
affect our dependent variable, and the
Yes.
alternate hypothesis is that some of the independent variables have a correlation with our dependent variable.
Exactly. That's great. So, Ankit, is that clear now? So, the F statistics and the significance of F, which is nothing but the p-value, the null hypothesis there is that there is no correlation between the dependent variables and any of the independent variables. There is no explaining power of any of the independent variables to my dependent variable. That is a null hypothesis. Alternative hypothesis is at least one variable or at least one thing, whether it's the intercept or cylinders or engine displacement or horsepower or weight or accelerate, has some explaining power to my dependent variable, right? And if the p-value is less than 0.05, you will reject the null hypothesis and accept the alternative hypothesis. Alternative hypothesis is that at least one variable has some significance, so I have a good model, right? So that is what we are looking at. Yeah. Hari is saying, will you drop X or Y RP? What do you mean, Hari? I mean, I don't know why you would say. If it is a bad model, then basically that means you don't have the explaining power. So let's say, I mean, Hari has a question. So let's say if the p-value comes out to be, less than 0.05, that means there is no explaining power at all, right, of the model. Then you drop it. Yeah? Go ahead, Nida.
Yep. After checking for f value and significance of f, we'll check our this table below here. We have the intercept, that's our dependent variable.
Yep.
I mean, where the like on y-axis where we are meeting the point, and then we have
Yes.
some independent variables over here. So first of all, we'll check for their p-value again. So we'll see if they are significant or not.
Right.
So here our p-value is like it's e minus raised power minus 50, so it should be quite smaller, less than 0.05.
Yep.
And then we'll check our t-stat value. It should be like less than or greater than mod 2.
Yep.
So it is 17, so that's greater than 2. So we're looking at the t-value and p-value, we say it's the significant. Intercept is significant for us.
Yep.
So we'll say yes. Then we'll look for cylinders.
Yep.
So here it is great, p-value is greater than 0.05.
Yep.
So we say cylinders is not a significant one. And also our t-stat, it is the value is greater than -2 and it's between -2 and +2. So we can conclude it's not a significant one.
Right.
Then we go for engine displacement. We check for our p-value. It's much higher than our alpha value, that's 0.05.
Yep.
And plus this t-stat value is also between -2 and +2. So
Yep.
it's again not significant. Then we go for horsepower. So here our t-value is minus 2.7, that is less than minus 2, and our p-value is like 0.0069, that's less than 0.05, so this one is significant. Then we go for weight, we check for t-stat, it's less than minus 2, it doesn't fall between minus 2 and plus 2, and then we have the p-value here, which is e raised power minus 10, and that's less than 0.05. So weight should be significant.
Yeah.
And then we have the accelerate. Here the t-value is between minus 2 and plus 2. It's 0.2, and our p-value, it is greater than 0.05, so it's not significant.
Okay,
So all
great. Okay, Nida, cannot hear you. Guys, can you hear me? Okay, so maybe some challenge Nida's end. Okay, so while we are waiting for her to come back online, does it make sense, everyone? Any questions from anyone? So this is, as I mentioned last time, linear regression is one of the most fundamental building blocks of everything else that will be happening down the road. So if any part is not clear to anyone, I'll be more than happy to spend some time. Richa, I know you were not there in last lecture, so you would have caught up on the video, but in case if there is anything that I can clarify, I'll be more than happy, right? Satish has a question. Satish is asking, can you please explain how F value determines the significance? Also, where does the minus 2 and plus 2 coming from? Sure, Satish. Rahul says, is there possibility that the t-stat and p value signifies opposite the same variable? What is the lower 95% Hari is asking, sir, I did not attend the last class. Satish says, sure, I will ask my doubt once I practice, Richa says, no problem. So let me take back the control and I will make myself the presenter. So you can see my screen, right? So the model that Nida just built, thank you, Nida, so much for that. So I don't know whether you can hear me or not. I think she may have dropped off. Yeah, I don't see. No, actually she's here, but maybe she's not able to offline. Yeah. Anyways, let's wait for her to come back online, right? So thank you so much for that. And there are a few questions. So let me just try to quickly rebuild the model so that you can see it on my screen, and I will obviously scribble on my screen as well. So again, this is a revision. So data, right? Data analysis. Regression, input range is gonna be your MPG, right? This is gonna be all the variables from here till here, right? And you will specify I have a label, 95 confidence interval is fine, and I will click on OK. Hi Nida, are you back?
yes, sorry, I got disconnected.
No problem, no problem. So thank you so much for that, Nida. That was great. So I'm gonna mute you, and I will just take it over from here. Yeah. Okay. So so there are questions. The question is, what is the significance of t plus minus 2, right? That was the first question. So if you remember, let me actually switch to the blackboard so you guys can see it better, right? Without any background. So if you remember, when we were talking about the normal distribution, you can go and take a look back at the video. So this was my normal distribution, and we said this is a symmetric distribution. The mu or the mean is in the center. Then we have plus 1 sigma. Sorry, this is minus 1 sigma, plus 1 sigma, and 68% of the observations are within this range, right? Then we had minus 2 sigma and plus 2 sigma, right? And we said 95% of the observations are within this level, right? Remember, right? So this is where the plus minus 2t is coming in. So when you say that the t value is going to be more than 2, that means your p, the calculated statistics of p is actually on this side, right? So that is how it is significant. No, that, sorry, not t. The t value is more than 2. So the 2 is over here. So t computed statistics is on this side, or t is on this side. So that means I am statistically significant in concluding with the 95% confidence levels that whatever I'm trying to test is significant, right? So that is the thought process. So hopefully that answered your question. I don't know. I don't. Let me see who asked that. Give me a minute. Um, okay. It was Satish. So Satish, hopefully that is clear now. Plus minus 2t. It's coming in, right? Cool. The other question, if you change the percentages from 95%, will it change the t-value? It will not change the, but the significance of that will change. So change the t, the alpha, because you're changing the alpha, now your t has to be plus minus. So if you change the alpha to, let's say, 99%, right? That I need to be 99%, or sorry, alpha is going to be 1 minus 99%, which is 0.01. If you change alpha to 0.01, that means now it is going to be plus minus 3 sigma that I have to be confident about. And the p-value has to be not less than 0.05, but the p-value has to be less than 0.01 in order to conclude the significance. Is that clear, Hari? Okay. Now the other question was on the confidence interval. So what are these confidence intervals, right? So these are the confidence interval for the for the coefficient that you're estimating. So let me just do the color coding. So I estimated the coefficient to be 46 with the error in the estimation of this. I am saying the coefficient will be lying between 55 and 41, right? And this is another way of testing whether something is significant or not. So so I will write it down so you can see it also. So if the 95% confidence interval, which is the lower 95%, so you're saying that I'm 95% confident that the coefficient is between 41 and 51. If the 95% confidence interval, which is represented by CI here, does not include 0, that variable is significant. Then the variable is significant, right? So let's look at this test. So does this range right here include 0? Who can answer? Does it include 0? So is 0 between 41 and 51? The answer is no. So is this variable significant or no? Yes, right. So if the range does not include 0, the variable is significant, right? So using this test, we will say that the intercept is significant. How about the next variable? Do you think this is significant or not? First of all, does it include 0? Does it include 0, this range? I'm color coding that in, let's say, some other color in yellow. It includes 0, right? So will it be significant? So remember, if it includes 0, this variable cannot be significant, right? So it's not significant. So you can see the t-stat, the p-value, the confidence interval, everything is telling you the same thing. So what does it mean it does not include 0 or it includes 0, right? So if the 0 is there, then you're saying with 95% confidence interval, I am saying the value could be between minus 0.12 to plus 0.4. It also includes 0. So in that case, the coefficient can be 0. And if the coefficient can be 0, then the variable is not significant, right? Hopefully that makes sense to you, right? If you can just quickly confirm why the 0 is such an important thing in the confidence interval. Right, okay. Nazia says fine, Ankit, okay. How to use this upper percent in business? I will talk about that, Hari. So just it will be sort of related to the heteroscedasticity concept, right? Similarly, this variable is not significant because it includes 0, right? This variable, who can tell whether this variable is significant or not? Just by looking at the confidence interval. Not significant, Richa says, right? Or significant? It is significant, right? Why? Because it does not include 0. This range does not include 0. The range that I'm color coding in red does not include 0. No 0. So it is significant. How about this guy that I'm color coding in blue? It is significant because it does not include 0, right? So, and you can do the remaining. So I think I have given you the hint. So there are multiple ways you can test whether the variable is significant or not. And one way obviously is t-stat, the other is p-value, and then the third one is a combination of the confidence. So these are basically 3 tests, and normally they should all tell you the same thing. Yes, they're all telling you the same thing over here as well, that whatever I'm drawing from the T, whatever I'm telling from the P, whatever I'm telling from the confidence interval, they are all telling me the same thing, right? Any questions before I switch gears and talk about the data and our exercise for today? Is everybody on board? Is there any possibility that t stat and p values signifies opposite for the same variable? Rahul says no. Rahul, generally it doesn't happen, and if it does happen, that means there is something wrong with the model, so you should not move forward with that. You should do some variable treatment or something else before you move on, right? Abhijit is asking, we calculate the significance of model based on calculations like R square and R and other variables which will be standard for each data sets. So is it the data set which decides how well the model can predict? More accurate the data, more accurate be the model. Yes, I mean, Abhijit, a large part of your model performance is dependent on how good your data is. So if you have the right predictor variables in your model, you will build a very good model. If you do not have the right predictor models, you will not have that, right? So that is the thing. Satish is saying, will we avoid non-significant independent variables in general? That is correct, Satish. That if a variable is not significant, you should not include that in your model, unless you have a very, very strong business reason, why we should have that variable in the model. Generally, we do not keep anything insignificant in the model. Any other questions, folks? Are we good? If you can quickly confirm yes, no. Okay, so everybody is comfortable. So let's move on, right? So if you go to the learners page for today, and let me try to navigate there, which is right over here, right? I have couple of data download. Sorry, I'm downloading the SAS R code first. That's fine. So download the Excel file or the CSV file on your end, and let's look at that. So there are two CSV files there, right? So let's download. Because I have already downloaded, I'm not going to do it. I'll just pull it from my drive here, right? But for you, I think you'll be required to download in case if you want to work along with me. So let me just navigate to the right folder. Right, so this is the data that we have. So what is this data? So this is the data on an insurance company. They are looking at the policies, right? So each observation is a policy number. Then we are looking at how many years of driving experience the driver has who has this policy, how many vehicles this driver has, what is the average age of the driver, what is the gender, so 1 signifies male, 0 signifies female, what is the marital status, 1 signifies whether they are married, 0 signifies whether they are unmarried, then we have the vehicle age, and then we have the fuel type dummy. And these dummies are already created for you, but when you look at the data, the actual data, and I think I have that also, so let me see if I can show you. Over here, right? So over here, this is the actual data that you will be having. So what you have to do is to basically convert these dummies to these categorical variables to dummy, right? So male is 1, female is 0, and so on and so forth, and that is how we will look into the final data, right? And then you will build a model on this. And what is it that we're trying to predict on this? We're trying to predict that if these are the policies where the insurance company had the losses, right? So each of these policy has some losses associated with that. So if I incurred some losses on the policy, what are the characteristics of the customers on which the insurance company is making the losses, right? And let's see how many rows of observations we have. So we have 15,291 observations, right? So this is the data that we have. Is the data clear, folks? Yes, no? Very quickly. Screen not refreshed. Can you see my screen or no? I think you should be able to see, no? Yeah. So I'm going to give it some time. Maybe it's getting refreshed. Okay, so let's pull up the code for R first. And before we go on, I mean, you had a homework, right? So before we go on to R and do this, you had a homework, and the homework was that you will read up what is there in the Word document. So how many of you did it? How many of you actually read something in the Word document? And who can explain what is a multicollinearity, what is a heteroscedasticity, if you understood some of these concepts? And it could be very, very wrong interpretation as well. So, I mean, the idea is not you to come prepared with that. The idea is at least you should be aware of that, right? So, does anybody want to try what is a multicollinearity? Nida says, I went through. Nazia says, multicollinearity I can explain. So, Nazia, I will unmute you if that is fine. Is that okay, Nazia? Yeah? If you can talk. I can write, Nazia says. Okay, that's fine. You can write, Nazia. That's okay. So you can write. I have a lot of sound. Okay. Arvind says multicollinearities when independent variables are correlated to each other, thereby affecting the results. Shall I unmute you, Arvind? Maybe you can educate us a little bit. Yeah? Okay, go ahead. I've unmuted you.
Multicollinearity is when independent variables
Uh-huh.
are correlated to each other in a way that it becomes difficult to get the predicted score.
Okay. What do you mean by difficult?
So, like, there is a lot of interaction between these independent variables,
Yeah.
and they affect each other's um, probability. I can say like
Okay.
the
Okay.
F act
Fair.
as a
Fair enough. Fair enough. Okay. Thank you so much, Arvind. Any other thing you want to highlight?
uh, so multicollinearity can lead to false positives and type 1 errors.
Mm-hmm. Okay. Okay. Fair enough. So basically, the model becomes a little bit shaky. It may lead into some more errors, right? Thank you, Arvind, for that. Okay. Anybody else who wants to try? Gaurav, how about you? Hari, Kaustubh, you want to try? Manmeet, shall I unmute you very quickly? You have the very good answer there. If you can talk on the phone, Manmeet. No voice. Okay, that's fine. So Manmeet says multicollinearity leads to difficulty in disentangling individual effects of correlated variables on the dependent variable. Okay, that's great. How about others? Who can talk? Rahul, can you explain if you read the paper? OLS method. Okay, Nazia says. Vineet, how about you, sir? You've gone through the lecture once. Do you want to talk, Vineet? Okay, good. So let's talk about the first concept, right? First concept is the concept of multicollinearity, and make sure, guys, that you read up before you come, because some of these concepts will be very, very difficult to understand, right? So I will put the discussion material for tomorrow's lecture by sometime early morning tomorrow. So make sure that you go through it, and that will be good as well, right? Um, so let's talk about what is multicollinearity, right? So moreover, it does not violate any of the OLS assumptions, but still might lead to misleading results. Thank you, Manmeet, for that, right? So let's talk about what is a multicollinearity. What is this beast at all, right? So multicollinearity, right? What does it mean? So let's say I'm trying to predict y as a function of my three independent factors, x1, x2, and x3, right? One of the key assumption in the model that we have, and the model's name is OLS, ordinary least square, is fitment. One of the key assumption there is that there should not be any correlation between x1 and x2 and x3 and x3 and x1. So x1 and x2 should not have any correlation. X2 and x3 should not have any correlation, and x1 and x3 should not have any correlation, right? So that is one of the key assumptions that we have in terms of fitting that model for estimating the line, right? So if you remember, we fitted the line like this, right? And the points may be like this, and the fitment of the line was based on the model called OLS, ordinary least square, right? So what we're trying to do here is we are just making sure that that assumption is not violated. And how do we really know whether it's not violated and violated? Is basically when we correlate the x1 to x2 to x3, right? And if you see a significant correlation between x1 and x2 or x2 and x3, we say that our model has a multicollinearity problem, and that needs to be fixed before we move on. Is this clear, guys, so far? What is multicollinearity? How do we test? Yes? Okay, everybody's on board. Okay, so, okay. So now somebody can ask the question in an interview to you, okay, what if I have the multicollinearity in the model? So what, right? As an analyst, you are supposed to be asking the question in big words, so what? Why should I worry about this, right? Why the heck I should worry about the multicollinearity and why this is going to be a problem for me, right? So this is what we will be covering now. So what happens? What are some of the challenges if you have multicollinearity in your model? Your estimates, the coefficient that you are estimating, right? So what are these estimates? These are basically your beta naught, beta 1, the intercept coefficient values, x1, x2, x2 coefficient values. They become very, very unstable, right? So what happens to them? They are very unstable. What does it mean by unstable? So for example, you may have built a model now, and for one variable, let's say this coefficient for factor x came out to be 0.3 for factor x1, right? What happens is if I add some additional data in my model, this 0.3 may change and look like 0.5. So I don't really have a very good sense whether it's 0.3 or 0.5. Or if you test your model, so let's say you built your model on data from 2014, and if I'm testing my model on data from 2015, again this coefficient can change into a weird number, right? So what it really means is that you really don't have a very good control on what is the real coefficient for each of the parameters that you're estimating. And what it really means is that your model is not good, because you really don't have a sense of what are the coefficients that you're looking at. So your model is not good, cannot be used because it's not a stable model. So basically what really the multicollinearity leads to the problem is the instability of the model, right? Because if the model is not uniform, I really cannot predict anything based on that. So the instability problem exists in my model, and that becomes a challenge for me, right? So this is the effect of that. So this is the effect or the influence of having the multicollinearity in your model, right? And you have to basically make sure that we mitigate that, right? Is it clear? Yes? Cool. Now, how do we detect multicollinearity? We talked about the correlation that we can do between the independent factors, and there is also a test which is generated in both R and SAS, and that test is called VIF. The full form of that is variance inflation factor. So there's a test which is generated in both R and SAS for VIF, and the rule of thumb is that if the VIF is more than 2, those variables are correlated and you should fix that, right? So this is the golden rule. It should not be more than 2. As long as the VIF for each of the variable is less than 2, you are good to go, and there is not a significant multicollinearity problem in your model, right? Is this metric clear, folks? Good. So this is the test for multicollinearity. If you have a multicollinearity problem, you need to fix that, right? Now, how do we fix that? I'm going step by step so that you're not confused when we are running this model in R. How do we fix that? So let's say I found out that factor x1 and factor x2, they are correlated, right? So, whatever happens in x1 also is influenced by x2 and vice versa. So these are correlated, right? So I can take, if they are heavily correlated, I can take only one of these factors and put that in the final model. So if my final model is, y as a function of something, only one of these guys can go in this function. They cannot be both there, right? So only one variable can go in there. Now, how do I decide which one goes in there, right? The one that goes in there, I mean, what we do is basically we say, let me build two simple linear regression model. So y as a function of only x1 and y as a function of only x2, and whatever gives me a better r square value. So whichever is a better predictor of my final dependent variable, I will take that and put that in the final model. Is this clear, everyone? Right? So this is how you do it, right? There are other sophisticated techniques which we will be not talking right here, like factor analysis or the principal component and so on and so forth, which can be used to reduce the number of factors and reduce the number of multicollinearity that you have. So, but I mean, the basic idea is precisely that, right? So this is about the multicollinearity. So with this, we cover this entire concept. So let me take a pause here and see if anybody has any follow-up question, but we have covered the entire multicollinearity rationale and what really happens. Can centering the IV avoid multicollinearity? What does it mean, centering the IV, Arvind? So Arvind says IV is actual minus mean. Does it cut off vary industry to industry or by organization? Manmeet is saying. Well, Arvind, I mean, that is more in terms of, I mean, it may have some impact, but, that is not necessarily an ideal fix, right? So you're better off sort of like looking at removing the variables, which may be collinear, rather than trying to recenter those variables, in my opinion. Manmeet has a question. Does the cutoff that we talked about, the VIF, vary from industry to industry or organization by organization? It may very well vary, Manmeet, but as a golden rule of thumb, I mean, in case if your organization or your company does not have any sort of cutoff on that, you are better off using a cutoff of 2, right? That is what the industry well accepted norm is, right? Okay, cool. So shall we move on? Yes, no? Manmeet has one more question. Yeah, go ahead, Manmeet. So while we are waiting for the question from Manmeet, let me clear up the screen and go to the next concept that I asked you guys to read about. And that concept is heteroscedasticity, right? So it's a mouthful, very, very difficult word to pronounce for most of us, at least for me. Hetero ski dash T city. Now, who wants to pronounce that on the phone? Who wants to try pronouncing this 5 times in a row? Any volunteers? So we have some volunteers. Richa would like to pronounce that. Go ahead, Richa. I'll unmute you.
Heterozydicity. Heterozydicity. Sorry. Heterozydicity.
No, no,
Heterozydicity.
it's no. It's actually heteroscedasticity, something like that. Heteroscedasticity, heteroscedasticity. I cannot
Heteros
pronounce it two times in a row.
Heteroscedasticity.
Ah,
Heteroscedasticity.
exactly. Yeah, that's great. That's great. Thank you, Richa.
Yeah.
Yeah, so this is the next concept that we are looking at, and it's basically heteroscedasticity. Heteroscad. So you have to read in different segments. So that's why I mean it's very very difficult for me to pronounce multiple times. So heteroscedasticity, heteroscedasticity, right? So that is how basically you pronounce that. So what is this? Is there any understanding that you guys have? I mean, who has read the paper? For the people who said yes, I have gone through the write-up. I mean, can you tell me what exactly this may mean? What does it really mean? So it's a mouthful, but I mean, it's not as complex to really understand. Heteroscedasticity is not that difficult to understand. What does it really mean? Some sort of pattern in error, Nida says, okay. The variation in y around the regression line. Heteroscedasticity says if residuals follow a pattern, it should be checked as best fit line is not working well. Should be same. So Nida, do you want to explain on the phone if I can unmute you? Yes? Up to you. Kaustubh says error between the actual and real values. Manmeet says the errors of the independent variables are uniformly distributed across each x variable, right? Okay. So I think all of you guys have read and you have very good understanding as well on that. So Manmeet gives me a new term, homoscedasticity, scadi, homoscedasticity, right? Which is basically the opposite of heteroscedasticity, which is homoscedasticity, right? And what it really means is basically one of the other assumption in the OLS model is that when I fit a line, so let's say I'm putting x here and y here, y is my dependent variable, x is my independent variable. This was the pattern that I saw in the points, and I happily put a line, right, like this. One of the key, and these are basically the errors, right? These are the errors that you have in estimating the line fitment. One of the key assumption in the linear regression model is that errors are randomly distributed. Randomly distributed along the x. So if I look at the x as a range, I should not see any pattern in the errors, right? So let's look at a new chart. So let's say if the model does not have this problem, and I plot my x, and instead of plotting the y on the y-axis, I will plot my residuals, or which is the error in estimating the y's. So if I plot my error should look like a group of bees, right? So I should not find any pattern. So this is what I think Manmeet was talking about. This is the homoscedasticity, right? That there should not be any pattern, right? This is the key assumption that we have in estimating the OLS model. Is this clear, guys? That when I look at the prediction interval of X, I should not find any pattern. Yeah? Okay. Now what happens in the heteroscedasticity is if I again plot my error, I will plot my error again, and again I'm looking at the error. What can happen if there is a problem in prediction of the x versus y is that maybe on this side you have less error, but as you are moving towards higher ranges of x's, your error keeps on going higher and higher, right? So that means my model is very accurate for this portion where the x values are beyond below a certain level. I have good prediction power here, or I'm having less error. But as I'm moving into the higher side of x, the error is growing, right? So that basically, again, just like the instability of the coefficient because of the problem of multicollinearity, now I have the instability of my error prediction. So over here, my model is more inaccurate, right? And over here, my model is less inaccurate, right? So Arvind says some of the Anscombe cortlet follow homoscedasticity. Yes, Arvind, right? So that is the concept. So is this clear, guys? I mean, what really it means and why there is a problem with the heteroscedasticity? So this is the main construct, right? So even though this is quite a mouthful word to say, and for me, I mean, I really cannot say it 2 times in a row. Forget about the 5 times in a row. Richa has been, quite good in pronouncing it, multiple times without any problem. So that's great. But something that we should always make sure that we are able to. What is the impact of homoscedasticity? Arvind is saying no impact. So that is the preferred solution. Heteroscedasticity is what we are saying should not be there. So Ankit is saying, sir, what is the solution of that, right? So I will talk about the solution and how do you really fix that. So if you want to manually fix the solution or manually come out with the solution of this, Ankit, we will have to transform our variables, right? So we have to transform our x and y, right? You'll have to try different combinations and see where exactly you see less error. But this is a very, very manual route and not the preferred way of fixing the heteroscedasticity. Both R and SAS have inbuilt tool for fixing that. So we will use that. Acha guys, now we are at 8 o'clock, just to be cognizant of the time. We have two different ways we can handle the class for today. So if we take a break, we will be able to wrap it up sometime by around 9:45. If we don't take a break, we can wrap it up by around 9:15. So which one is it that you guys will prefer? We can continue till 9:15, wrap it up at that time, or we can take some break in between and then wrap it up a little bit later. So Kaustubh says wrap it up by 9:15. Hari says no break, 9:15, 9:15, 9:15. Okay, so I think most of you are quite enthused by the idea of no breaks and then continuing till 9:15. That's great. So we'll do that, right? So we'll spend maybe 1 hour, 15 minutes more on this and then we will wrap it up, right? I know some of you have joined a bit late. So Dimple, if you have missed out some portion, so you can catch up on the video and you can join at 6:45 tomorrow. So I don't know how many of you have noticed that, but we are actually meeting every day when there is a class at 6:45. So I'm available at 6:45 p.m. tomorrow as well. And there is no more class from Amit until the next several weekends. So tomorrow again I will have it on a different topic, right? Amit has wrapped up his portion, so I'll be continuing with the more advanced topics now. So tomorrow, again, you can, I mean, in case you watch the video and you have any problems, you can be there as early as 6:45, and I'll be more than happy to explain any concepts that you may have some doubts about. Yeah. So this is a benefit for you. You can benefit from that. I mean, this is an opportunity for you that you can benefit from. Yeah. Okay, so before I move on, is the concept of heteroscedasticity and the multicollinearity 100% crystal clear to everyone? One more time, yes, no? Clear, Nida says. One more time, Hari. Yes, it's clear, clear. Multicollinearity, one more time, Ankit says. I had a network problem, Hari says. Okay. Hari and Ankit have some thoughts on that. So who wants to explain the multicollinearity and the heteroscedasticity? Nida, do you want to do that again for the benefit of Hari and Ankit very quickly? Just maybe in few lines, and then they can obviously watch the video, or I can explain later on. Ambuj have to try doing through video multiple times. No problem, Ambuj. I mean, I think these are some of those things that you have to take some time to really do it, right? So I will unmute Nida. So if you can just um, repeat, the multicollinearity and the heteroscedasticity concept. Nida, go ahead, please.
Hi, RP, can you hear me?
Yeah, I can hear you. Please.
Yeah, about multicollinearity, it's like when there is one dependent variable, there are multiple independent variable, and there is some sort of strong correlation between the independent variables. So in that case, it becomes very difficult for us to predict the coefficient of each
Yeah.
independent variable and how they are impacting our dependent variable.
Mm-hmm.
So,
Yeah.
and when we have multiple variables that are correlated to each other, in that case, we should just pick one of them, not all of them, so that we can see the actual impact of the independent variable on our dependent variable, MPG, whatever it's in our case. And
Right.
about heteroscedasticity, I'm sorry, I cannot pronounce it.
Try it one more time. Try it.
Heteroscedasticity, no,
Yeah.
heteroscedasticity,
Heteroscedasticity.
okay,
Yeah.
yeah,
Huh. Anyway, so you can move on. Yeah.
yeah. So in that case, we have something called as residual, or sometimes residual, I think, is the square of errors, or the
Mm-hmm.
errors. We see some sort of pattern in the errors, like
Sure.
maybe it could be increasing or it's decreasing as we
Sure.
move ahead in our observations.
Yes.
So yeah, when there is that some sort of pattern, that's
Yes.
not good for to predict our model.
Yeah.
So we need to remove both multicollinearity and I'm sorry again.
Heteroscedasticity. Yeah.
Yeah, from
Uh-huh.
our model.
Yeah.
So
Okay.
yeah, so here we were talking about how do we remove the heterogeneity, like if there
Uh-huh.
if
So,
there
so,
are,
okay. Thank you, Nida. So, if there is a pattern like this in my error, is there a problem or no?
yeah,
How
there
many?
is a problem.
There is a problem, right? I mean, would everybody agree with that? Right? So it doesn't have to be linearly going up or linearly going down. As long as there is any sort of pattern in the error, there is a problem. You should not see any pattern in the error. It should be looking like a swarm of bees, like all over the place, right? So as long as you see any pattern in the error, I mean, you got a problem that you need to fix, right? So that is the concept of the heteroscedasticity that Nida was talking about. Multicollinearity, Hari and Ankit, is basically when you have the correlation between the x's, and that we have to fix, and you can replay back the exact video segment. I mean, you can watch there, but the bottom line is that one of these guys will go in the model, and the variable which has the more prediction power for the dependent variable will ultimately make it to the model and not the other guy, right? So that is how the concept is for the both of these key things that you have to be aware of. Yeah. Thank you, Nida.
Thank you.
Okay. Any final questions before we move on? Shall we go ahead with the R code then? Okay, so we will first build this model in R, right? And you guys have some, hands-on work in R, and you have practiced some assignments, so it should not be a real surprise for you. So what are we doing over here in the portion that I've highlighted? Setting directory, Hari says, right? Why do we have to set the directory? Nazia says setting directory to fetch the file. Nida says setting the working directory, path where the file lies, setting the location where the program will be saved, files will be fetched from. Subhapata says. Nadia says everything is located there. Yeah. So basically your input, output, everything you're saying will be located in this location. This location is on my desktop. See users R Pandey, desktop documents, classes, blah, 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 right? So I'm going to set up this working directory. But before I do that, let me clear up my entire workspace and you can use these brushes. So it's going to remove all the files which I'm not working with right now, right? And over here, you can do Control L. So paintbrush there, Control L here. This will clean up the entire slate and you are good to go, right? Thank you, Arvind. Default directory for the read location. Yes. So let's go ahead and do that. So the working directory has been set. These are the two packages, right? These are the two packages which will be required for you to build the linear regression model. The first package here is lmtest. The second package is cars, or car, sorry, not cars, car, right? C-A-R. These are the two packages which are required. So if you don't have these packages installed, what will you do? You will do install.packages, right? So you'll have to first install them. So you will do install dot packages and install these packages, right? You have to put them in the double quotes and then put the name of the package and you have to install them, right? That is what you'll be doing. Getting error package not found. So that we will be able to handle. So just make a note of that. We'll be able to do something about it, right? So you may have to require the dependencies or load the dependencies like this zoo and so on and so forth. So anytime you have a problem loading up the package, you have to make sure that you are installing the dependencies as well, right? So in my case, the package has been installed, so I'm good to go. Next, what we are doing is, who can tell me what is there on line number 8? We are reading the file in, right? The file is located where? In the working directory, right? So we are reading the file, reading the CSV file. So we are doing a simple read.csv and able to read the file, right? Let's give it a minute. Is the file read? Yes, right? The file is read because I can see over here, it is telling me the information that there are 15290 observations and 9 variables and so on and so forth. So it's telling me that the file is read, right? How do I view the data? I can do view default data and basically it will be popping up this entire thing for me. Yes. So you can see that the data that we saw in Excel is reflected over here as well. And we are good to go, right? So let me go back here. Now let's do some data checking. So what are we doing over here in line 15 and 16? What is line 15 and what is line 16 doing? So Ambuj says first 6 and last 6 observations. Hari says head is first row. Gaurav says top 5 observation. Nazia says and last few observation. Kostub says first 6 elements. Tail is last row. Hari says Manit says checking first 6 row and last 6 observation. Kostub says last 6 elements, checking top 6 and bottom 6. Dimple says the correct answer, and Nida says printing top 6 and bottom 6 rows. The correct answer is the top 6 and bottom 6, right? So whoever said that, that is the correct answer. Head will by default print the top 6 rows. Bottom will by default print the bottom 6 rows, right? So this is what is printed in the head. You can see there are top 6 rows printed. in the head command, and there is basically the bottom 6 rows printed over here in the tail command, right? By default, it is the 6, and we talked about if you want to print more than 6, I mean, you can do that. It's there, part of the first video, our introduction. So you can go and see if you want to print more rows, how can you do that, right? What are we doing over here in line number 19? We are getting the summary of the data. So basically, it's gonna give you the summary of how many variables, what sort of things, and so on and so forth. So let's do that. So you see that, right? So summary age, it has given you the minimum first quantile, second quantile. So for the numerical variable, it will give you the quantiles. For the categorical variable, it will give you the frequency. Like for married 7783, single 7507, and so on and so forth, right? So that is a thought process, that for the numerical variables, it will spit out the quantile summary, and for the categorical variable, it will tell you the frequency, right? What is it that we are doing in line number 22? Hari says box plot. Ambuj says plotting. Dimple says generating the plots. Yes, exactly. So that's plotting. And Nida says plotting the graph, right? Scatter plot, Arvind says. So let's go ahead and do that. And there you are, right? So I have just plotted my default losses, and this is how it looks like, right? So if I click on the zoom window, I can open that in a new window, and this plot becomes magnified, and you can take a look at the plot. Now, what will be your observations looking at this plot? Any observations? So Hari says homoscedasticity. Dimple says there are outliers. Richa says there is no pattern. Nazia says some of the outliers. Ambuj says maximum losses are near 500. Kostub says heteroscedasticity. Nazia says at 500 there are many outliers. Ankit says 400 losses as the median value. Losses are max. Losses are mostly consistent between 0 to 1500. Urban says. Nida says some outliers are there, right? So there is no concept of homoscedasticity or heteroscedasticity here, because you're not predicting anything at this time. There is no predictor, you're just plotting one variable. But the correct observation is that you are finding that most of the data is centered around this level, right? So you see that, like very, very dark area over here. So most of the data is centered, below a certain level, but there are some observations which are, sort of like higher up, right? And these are what we call as outliers, right? So there are observations which are way above the other things. But how do we really define the outliers, right? And I think some of you were talking about this concept that how do I really know there are outliers, and how do I treat them, and so on and so forth, right? So what we are doing in this next step is basically we are creating the quantiles. And I covered this in the introduction to R when we did that. So we want to create the quantiles. So the first parameter that you have to pass on in this function is the name of the variable. So I want to run the quantiles on the losses, and I want to build these quantiles, right? What are those quantiles? So I want to have 0 percentile, 5th percentile, 10th percentile, 25th percentile, 50th percentile, 75th percentile, 90th, 95th, 99th, 99.5, and 100 percentile, right? Is this syntax clear, everyone? Okay, so let's go ahead and run this code. So it has exactly given you that, right? So let's look at this data over here. So when I ran what I have highlighted in the upper box, I get this result in the lower box. Now, if you remember, we talked about the outliers and how to fix the outliers. And we talked about, as a rule of thumb, we like to floor things at the first percentile. So anything which is lower than the first percentile, we floor that. And we cap at anything which is higher than 99th percentile. So any observations which are higher than the 99th percentile will be brought back to 99th percentile, right? So what is the 99th percentile for the losses? Looking at the lower box. 1204, right? So for the sake of simplicity, I don't have to be that precise. I can say I want to cap things at $1200. So if I have losses more than 1200, so if I have a observation, if I have an observation where the losses were, let's say, 1500, I will say wherever you see losses higher than 1500, bring them back to 1200 because I want to fix my outliers. Is this point clear? How we are fixing the outliers in my dependent variable? Yeah? Good. Good. So how do we do that? So I will talk about that particular step. How do we do that, right? Why are we capping and not removing the outliers? Generally, we do not remove the outliers because you will lose out the information, Arvind. So that's why, I mean, wherever possible, you should floor and cap and don't throw out the data, right? That is how it works. So let's look at the next line of code, which is over here. And I will put a box around it so you know what I'm looking at, this area. I'm defining a new variable called capped losses. And I am running a condition. So if else is how you run the condition, as I explained in the first lecture on R. So I'm saying if the default losses are more than 1200, make them 1200. Otherwise, retain their original value. Let me pause and make sure that you are able to get this in your head. Is the code clear? How we are capping that, how we are defining a new variable? Nazia, Subhubrata, Dimple say yes. Are you making outlier value to 1200? Yes, Gaurav, that's exactly what we are doing. We are making all the outliers equal to 1200. We are capping them at the 99th percentile as we discussed. Right? Syntax is very simple to follow. If the default losses are more than 1200, make them 1200. If they are not equal or not greater than 1200, if they are equal to 1200 or less than 1200, they will continue to retain their original value, right? So let's do that. So let's highlight this code and run it, and it has run. Now, do you see any change in this? And what is the change you see? What is the change, Subhaprita? New column has been added, right? New column has been added. So let's open up the file and let's look at the new column. So yes, indeed, there is a new column called capped losses that we created, and it has certain values, right? So let's look at the distribution of capped losses now and see what the distribution looks like, right? So let's go back to the code, and I will, I will type here in the interactive prompt. So I will say summary of default data dollar cap losses, right? Now, what is the change you notice? So actually, let me do both of them. So let me put the original variable as well. Default data. Original variable was called losses. So now what is the change you guys notice? Looking at where the box is. So the first one, which is over here, is the treated one. The second one is the original variable. So Nazia says now we have max 1200 in the capped variables. Does everybody see that? Yes. There is a slight difference in the mean, right? That the mean has gone down. But is there any change in the median? No, right? Because if you remember the first concept that we discussed, mean, mode, median, we said if there is an outlier or if there are outliers in your data, median is a more robust metric of the centricity because it's not sensitive to the outlier. So you can see clearly, even though when we have removed the outliers, my median does not budge at all, but the mean has taken a hit, right? And the other quantiles are not changed as well, right? So this is how you do the flooring and capping and making sure that your data is free of the outliers, right? So now you can see, how some of the basic building blocks that we talked about earlier on are actually now fitting into the modeling activity, right? So they were not some abstract concepts that we talked about, but they are actually being used for something in the modeling activity, right? Fair enough. Everybody's with me so far? Okay, good. Manmeet has a question. One question, can we throw some light on missing value treatment as well? Manmeet is asking. Arvind is saying, what is the index variable on the x-axis? As this data is quite clean, it is required, it is not required here. Manmeet is asking. So a couple of questions before I move on. So Manmeet has a very good question. Okay, what about missing values, right? In this case, because I do not have that many missing values, I mean, we are good to go, right? So in this case, for example, there's nothing missing, right? But if there is a missing value, what do we do, right? So that is the first question. And the second question, I think, Arvind, you have is what is the index on the x-axis? This is nothing, Arvind. This is just basically the row number that you're looking at and just the, the variable plotted here. So this is not a bivariate. I mean, even though it's plotted like this is a univariate. So again, going back to something that we discussed earlier, this is a univariate analysis. I'm just looking at one variable plot here, right? Now going back to the question that Manmeet is asking, and you will see that Manmeet coming in some of the future lectures, is basically missing value. If you have missing value, so for example, you can say like this. So if default data dot losses is NA signifies missing value in R. If it is NA or if it is some bogus value like 999, so a lot of times in the database they will put some bogus values like 9999, right? Which basically becomes a placeholder for the missing value. So you can just write a simple code like this. So if the default losses is NA, or if the default losses is 9999, we replace them with what? Replace them with either the median or with the mean. That's how we usually do. So when you have the missing values for a numerical variable, you generally go ahead and replace them with the mean or the median. So obviously if you have the outliers in your data, you will replace them with the median. Otherwise you can replace them with the mean, right? This is for the numerical variable. For categorical variables, so let's say I have the city name, right? And there are like different cities. So there's a city called Delhi, and then there is Mumbai, right? And then we have New York, and then I have city missing, right? Now, how do we handle those? How do we handle these missing values, right? So then you can see, I mean, what is the most frequently happening value? Is it Delhi? Is it Mumbai? Is it New York? So let's say Delhi happens to be the most frequently happening value. You can go ahead and replace this value with Delhi. That is how it works. Or you can even go to the extent and say city is missing, in this case, and that becomes an entirely new category by itself. That is how we actually handle the missing value, right? Yeah, mode. Yeah. Satish is saying I'm clear with the code, but not clear why we use the 1200 here. We use a 1200 here because we are doing the capping, Satish, at 99 percentile. So whenever you have any outliers in your data, there's a concept called flooring, right? What is flooring? So any value which is less than 1 percentile will be brought back to the first percentile. Similarly, there is a concept of capping, that any values which are higher than 99 percentile over here, they will be brought back to the 99th percentile, right? This is the concept of flooring and capping, right? And that's what we are doing over here, that we are flooring and capping. In this case, there's no need to floor because there's no outlier on the downside, but we are capping at the 99 percentile. Yeah, Satish? Good. Cool. So guys, let's move on, right? What are we doing over here in line number 35? We are creating new data sets with all row, taking all columns but one in ninth column. Right, that is correct. So thank you all for answering that question. So we are removing basically column first and column ninth. And what are column first and column ninth? So if you look at this data, column first is nothing but the policy number. I do not need the policy number for prediction. So that's why I'm removing that. And I'm removing column ninth, which is the losses, because I've already created a new dependent variable, which is the capped losses, right? So I'm removing that from my data that I'll be using for the modeling, right? So let's go ahead and run that, and you can see clearly the number of variables have gone down by 2 because I removed that, right? Now over here, I'm gonna generate several different plots, and this is bivariate plot. So for example, I want to plot the age by capped losses, right? So if I go and click on it, you can see the plot is generated, and here you can see there is a pattern, right? Here you can say that there is a heteroscedasticity problem, there is a problem in terms of the prediction, right? Why? Because if I plotted two variables over here, the pattern is looking like this, right? So there is some sort of trend in between the two variables. So if I build a line, I mean, even if I fit a line like this, I mean, it's gonna have, more error here, less error here, and then somewhere in the middle, some sort of like in between error, right? So clearly there is a pattern here, right? That we need to fix. Similarly, I will do for all the other variables. Now, for the categorical variables, by default, when you say plot, it will plot the box plot. For continuous variable, it will do a scatter plot, right? So let me just quickly skip through these charts, right? So this was the first one that we did. This is the second one with the driving experience. Again, same trend. This is the number of vehicles. This is the age, the gender, whether somebody is a male or female, and then what are the losses we are looking at. So on the x-axis, you have the gender. On the y-axis, you are looking at how much is the losses that they are making, right? Again, the marital status and what are the trends we are looking at there, right? And some other parameters as well. So this is very interesting. This is the type of fuel. This is diesel, this is petrol, and whether losses are higher for diesel and lower for petrol, that can be seen, right? So this is plotting the data is absolutely very, very important before you sort of like move on with anything else. Now, now these variables like the diesel and petrol, they are the categorical variable. You will have to convert them into the continuous variables, right? And how would we convert them? Again, we will be doing something similar to what we have done over here. If the the fuel type, if I remember the type of the variable. You can actually look at the variable description by this arrow. It will expand that. So you can see, yeah, the name of the variable is fuel dot type. So you can say if fuel dot type is equal to D, I want to code that as 1, else 0, right? It will create those dummy variables for you, and you can call that fuel dummy, right? I have already done it, and that is the other data I showed you earlier. So I'm not going to do it in interest of time because I have to do this activity in the SAS as well. I have already created these gender dummy, married dummy for the categorical variables. Capped losses, I showed you how would you create that. You can follow the same template to do it for these two, and that will become your homework as well, right? Arvind says, how can we say heteroscedasticity by looking at these plots as they do not contain residual? Even though they do not contain residual, Arvind, you notice a trend. You notice a trend. So if I put a line like this, that line may not necessarily have the same error, right? So you can see the error. I mean, even if I put a hypothetical line, you will see that, but I mean, it will come by experience that you can see that even if I put a line on this data, there's going to be some sort of error non-uniformity, and that points to the heteroscedasticity. Don't worry about it now, Arvind. We will have a test for it. Okay, guys, so we will directly import this new data. The new data is basically having all the dummy variables created. Everything is good to go. So I've imported that data, and that data is called default 4, right? So I will just, for the sake of making sure that you are clear, I will show you this data. So now I don't have the M or F or D or P for the fuel. I have the gender dummy and I have the married dummy, and then I have all the other variables that we're looking at, right? So that solves my problem. And then first thing I will do is to create the VIF. What is VIF? VIF is the variance inflation factor, a test for the multicollinearity. And when you're creating the VIF, actually you are running the regression itself. And the function to run the regression is LM, linear model. LM signifies the linear model, and this is the part of the package that we've already installed, which is the LM test earlier on, right? The syntax is very simple. You say what is your dependent variable. So cap losses is my dependent variable. Then there is a tilde sign. Then you are having your independent variables. One independent variable. Then you have the plus sign. Then the next independent variable. Then you have the plus sign. Then you have the next independent variable. Then you have the plus sign, and so on and so forth. And in the end, you are specifying the name of the data, right? So this is how you are creating that object called VIF data. Or basically you're running a regression on this, right? And you're calling that data or that object as the VIF data, right? Let's go ahead and run it. You will not see anything. So it has basically created that object over here. Now, if I have to check the VIF of this data, this is how I will go and check. So you have to say VIF of the data that you have created, and then it will state the VIF. So let's go ahead and do it. There you go, right? So now you have gotten the VIF, the variance inflation factor for each of these variables, right? We haven't used space in variable names. Is it necessary to run LM? Yes, LM is the function that you'll be using, Arvind, to run the linear regression model, right? So now you have the VIF generated over here. Now, which variables are correlated? So remember, the rule is more than 2. So which 2 variables are the correlated variables here? What would you say, looking at the VIF values? So all of you are pointing years of driving experience and average age. They seem to be correlated. Does it make sense intuitively why they should be correlated? Yes, Nazia says, right? Because more my age, more the years of driving experience I'm gonna have, right? And vice versa. More the driving experience I have, chances are very good, higher age I will be in, right? So they are correlated. So that means only one of these variables will finally go in the model, and not both of them. So how would I fix that? So remember, we said we will build two different models. So the first model I'm building is with the capped losses and average age. The second model I'm building is capped losses and years of driving experiences, and I will look at their summary, right? So let me build this model first, which I'm storing in the object called age 1. And the second model is with the driving experiences. I'm trying to fix the multicollinearity problem here. And then I'm going to summarize. So if you want to look at the summary of your model, you say summary of the object that you created. So summary of H1, it will show me the entire model, right? So now this may look familiar to you. So it looks similar to, what you created in Excel, where it's saying, what is the model that you have built? What are the coefficients, what is the p-value, what is the t-value, what is the standard error, what are the estimates or the coefficient, just like what you have done in Excel, right? So in this case, and then over here you see the R square value. So the adjusted R square value for the age is coming out to be 0.26. Let me make sure that I make a note of that. So for age and the capped losses, the R square is 0.26, right? Now let me go and do it for driving experience and then look at what is the R square there. So in this case, for the driving experience, the R square is coming out to be 0.19. So which variable do you think we should put in the final model? Age or driving experience? So Nazia think it's gonna be age, Hari says age, Arvind age, Ambuj age, Subhapratai age, Rahul age. Everybody says age, right? Good. The age, right? So that is the concept, right? So you basically just verified that both of these are collinear, and I will only be able to plug one guy in the model, and I will just take age in that case, right? So that is how basically you remove the multicollinearity and you remove the um, years of driving experience. Now, what have we done? Now we will build a model again, but this time I will not have the other variable, the driving age, right? I will have only this, and I will rerun this model, and that model has been generated. I will look at the summary of this model, right? And the summary of this model is stated over here. Let's take a look at this summary. So I ran the model with the average age and not the driving experience because they are collinear. So I have a question from somebody. Arvind has a question. Yeah, Arvind, go ahead. I have unmuted you. Arvind? Hi, Arvind.
We have very low R square value for both.
Yeah, because
Should we be
because it's
including
just
them?
yeah, definitely. Because you're just looking at one factor. So one factor may not necessarily explain everything that happens in your model, right? So that's why, I mean, here you do not look at the R square value to see whether that should belong in the model or not. You should be looking at the t value and the p value. And as long as those values are significant, then they should be part of the model. Yeah. R square is for the overall model and not for the individual factors. Okay, so this is how the final model came out, right? So this is the model that I fitted, right? And basically it gives you the residual, min. So how much is the error? It gives you the range for the error. And this is where it gives you the estimates for each of them and the t value. So looking at the t value, which variables are significant, which variables are not? All except number of vehicles, Abhin says. Number of vehicles is not significant. Gaurav says except number of vehicles, everything is good to go. Everything else is good to go. Abhijit says number of vehicles is not significant, everything else is good to go, right? So good. So everybody sees that. neither says except the number of vehicles, right? So everybody sees this. I mean, and it's exactly similar to what we have done in Excel, right? So it's not any different from there. And similarly, you can look at the p-value over here, and that tells you exactly the same thing. All of these guys are very, very significant, and except that number of vehicles, right? R also gives you one more visual way of looking at the information, which is the star system, and that is defined over here. So if you have more stars, those variables are very, very significant. So basically, this is like almost 100% significant variables, right? 3 stars. 2 stars are going to be 99.99% significant, and so on and so forth. So you can follow the math in terms of how those stars are, and just by looking at the stars you can see which are the significant variables and which are not. So there's no star for this poor guy, and that has to be thrown out of the model, right, when we are building the final model. If we include years instead of age, will we get a lower R square of the model? Arvind says yes, you will get a lower R square. You can try to do that as a homework, right, and you will be able to do that. So, Manmeet, did I answer your question by looking at the p-values, or you still have that question? Okay. So now what we'll be doing is basically we will remove the number of vehicles because it's not significant and rerun the model. Okay. Rerun the model, and then this is how the model looks like. Now all the variables are significant here, right? And everything looks good. And if you see the R square, Manmeet says, I mean, I cannot compare exact values. No, I mean, you can compare exact values because see, alpha here by design is 0.05. So anything which is less than 0.05 is significant. So all of these are significantly lower than 0.5, right? So these are, very, very low values. So they're all significant p-values, Manmeet, right? So if you notice, even the R square value has gone up when we threw out the variables which are not significant, and that is, a gain that you make when you throw out the not significant variables from the model, right? So this is how we do it. Now we have fixed the multicollinearity. We haven't talked about the heteroscedasticity yet, right? So now there is a test that we do, and that test is, or the function name for that is called the BP test, and that test for the heteroscedasticity in your model. And if that value, p-value for that test is less than 0.05, that means there is a heteroscedasticity in your model, right? So in this case, when I run the BP test, which is the test for heteroscedasticity in R, I got the p-value less than 0.05. So that means, yes, there is heteroscedasticity in my model. Is that clear, guys, how we did it? This is the intrinsic function built in R for doing this test as part of the LN test package that we've installed. This is BP test, right? And we did it, and we found out that p-value is less than 0.05. So there is a heteroscedasticity in the model. And in the next steps, we'll be talking about how we want to fix it, right? The fix of that comes in from a package called Sandwich, right? And you can do even the LM test, and the math beyond math, how it fixes the heteroscedasticity is basically a concept of matrix rotation. If I try to explain that, it will be, the entire day, how the matrix is being rotated and how it basically fixes that, right? So, but the concept behind that is that it changes the way variables are defined. It redefines the variable, it transforms those variables because of the matrix rotation. Those variables are not necessarily going to be, have that sort of error distribution, right? So if you do this in the end, run this entire thing, you will get a new estimate of the variables, right? So what I've done is I have said, I have ran basically the same object, and we have defined that I want to fix or I want to do the rotation of type HC4, which is a fix for the the heteroscedasticity. And based on that, you get the new estimates of all these coefficients. And now these coefficients are your heteroscedasticity proof coefficients, and you are good to go with that. And that is how you have fixed both multicollinearity and heteroscedasticity in the model, and you are good to go with these, and you can build an equation and you can make predictions about that, right? No, it does not tell you which factor is causing the heteroscedasticity. That you'll be able to see from the y by x plot, Arvind. But it tells you that overall your model has a challenge, and that can be fixed using what we are doing over here, right? There's not much to be discussed in this because it's quite a straightforward transformation you are doing. But the math beyond that is actually the matrix rotation, Gaurav. So all of this is, it's doing the matrix rotation, Gaurav, on line number 91 and 96. And it's trying to estimate the coefficient after you have done the matrix rotation. And what basically it means is that your variables are getting transformed, right? So whenever the matrix is changed, you multiply, you divide, you do certain things. So they are actually getting transformed in the process. And that is how basically it's fixing that. You can manually transform as well. So for example, you can create those ranges. So instead of looking at, this, you can create this range, and then you can create this range, and then you can create this range, right? So that way you can actually sort of like streamline the error that you're getting. But that is how it changes that. Fine. It does not impact R square. What it impacts in terms of this rotation is the coefficients here, and that is how you fix that, right? So guys, any questions, any further questions on this? So I will suggest that you build this entire model on your own, and you go step by step. And in case if you have any problem, ideally be there in the class tomorrow 15 minutes earlier, and I can explain those. But if you want, you can send me a note and we can discuss. Again, it's a reminder that tomorrow again I'll be here in the class and we'll be talking about the logistic regression, and that we can discuss, or I mean, before we discuss the logistic regression, we can talk about this. So before I move to SAS, is there any question? Because I do want to spend 15-20 minutes in SAS as well. Are we all good? Yes? No? Maybe? How many yes? How many no? How many maybes? Yes. So we have a lot of yeses. Kaustup says maybe. Ankit says maybe. Richa says maybe, need practice. Yes, Richa, agree. You need practice. Arvind, can we take a small break? It is getting heavy. Arvind says, okay. Guys, do we want to take a break or we want to continue and do SAS? I mean, I'm fine either way. Gaurav says no. I need to go through video once again. Ankit says 5-minute break, sir. Gaurav says continue. Ambu says break. Okay, so I think a lot of people are saying break. Nazir says no break. Well, now I have to use my veto power because now it's a 50-50 verdict. Or maybe some others can vote. How many for break, how many for no break? I can go on to SAS and we can finish up, and then I can try to wrap it up by 9:15. No break, no break, no break. Finish now. Break. No break, no break. Break. No break. Okay, guys. So I think, I mean, just in interest of time here, let's do a middle ground. So rather than taking a very long break, let's just take a 5-minute break. So this is 8:55. Be back by 9 o'clock, and we will try to finish the SAS by 9:20. So we'll extend the time that we finish the class by 5 minutes. We'll be finishing by 9:20. So let's take a 5-minute break. Okay? Be back sharply in 5 minutes. Okay, is everyone back? Yes. Richa, Abhijit, Hari, thank you. Vineet, Gaurav. Hari. Shall we start in interest of time? Nida, yes, okay, thanks. Kaustubh, okay, so I think we can begin. We can begin. I mean, I think as I promised, I will try to wrap it up a bit earlier today. So let's switch gears and let's go to the SaaS environment. And we have the exact same data in the SaaS environment that we'll be building a model on. But the process is a little bit difficult. I mean, not difficult, different, I mean to say, but not whole lot, right? What are we doing over here? And I don't know who is on. So maybe Nida, I will mute you so I hear some background noise. Yeah, okay. So what are we doing over here in the SaaS? And I mean, I think for some of you, what we have noticed is that doing both SaaS and R becomes confusing. So we will be just doing the linear regression in SaaS because some of the other modules will not be very easy to grasp in both SaaS and R at the same time. So just for today, we'll be doing both in SaaS and R. And from moving next lecture onwards, it will be entirely based in R, right? So we are setting up the library name, right? This is important to tell where exactly your codes are gonna be, right? We will import the file, but I have already imported the file, and I think we talked about this in the lecture last time. How do you import the file, right? Proc import, and we talked about the detailed comments and everything like that. So we will not focus here. The first thing like we did over here is basically run the correlation. So the procedure for that is proc cor, right? Proc is a short for procedure, cor is a short for correlation. You have to tell the name of the data, which in this case I'm calling my data as linear, right? And these are the variables on which we are running the correlation. So the only thing when you're running the correlation is you have to make sure that all these variables are numerical variables, right? So let's go ahead and click on it and run it, and we'll look at the output, right? So 8 variables we have used for the correlation procedure, right? And first of all, it gives you a summary of these 8 variables, like what is the mean, standard deviation, sum, minimum, maximum, all of those things are populated there. All of them have the same number of observations. There is no missing value, right? Then over here is where you are seeing the correlation. So the diagonal is basically the correlation of the variable to itself, right? So cap losses to cap losses obviously is going to be 1. Years of driving experience to years of driving experience is going to be 1. Number of vehicles to number of vehicles is going to be 1. Just like what we did in R, similar thing here, right? But these are the values that you should interpret, right? So over here it says cap losses versus the years of driving experience. There is a negative correlation of 0.44157, and the value over here is basically the significance. It's again with the significance alpha of 0.05 by default. You can change the alpha. So if it is less than 0.05, that means there's a significant correlation, right? Significant correlation. This, for example, you can see the p-value here is 0.20. This is not significant with the alpha of 0.05. And even you can tell from the value of the correlation coefficient as well that this is not significant, right? So hopefully that sort of clarifies. And even in this case, you can see SAS is good enough to give you the null hypothesis. Null hypothesis H naught says there is no correlation. Rho is equal to 0. Rho is the coefficient of correlation. That is 0. That is the null hypothesis SAS is assuming. And whenever the p-value is less than 0.05, you will reject the null hypothesis. You will accept an alternative hypothesis that there is a correlation, right? So you can look at the table, and that basically gives you a quick visual of which are the variables which are correlated, which are the variables which are not correlated, right? And this entire code, folks, is also uploaded. Let me go back. to the 3rd September folder. This code is also uploaded here in the same location, in the website on the learner's site, and you will see that the entire SAS code is there. So you can give it a try when you have time, right? But at least at a bare minimum, you should try the R, because R is what we'll be using predominantly, right? I will be plotting some of the variables. The procedure for that is sgplot, right? So you select the data and say histogram. I want to do the histogram on the cap losses. I want to have the y-axis the grid, and I will do run, right? So let's go ahead and run it. So there you go. So it will basically, so because I'm looking at that variable that we have already, or the data that we've already capped, so that's why you see there is a peak here at the 1200, because all the observations which are higher than 1200, I have capped them to 1200. That's why you see the peak and rest of the observations, right? So hopefully that is clear, right? Everyone, are you with me? Yes? So far? Okay, cool. There's a positive skew. Arvind is right. Yes. Similarly, I can look at the losses. I mean, the original variable that we had, the uncapped one, and you can see there's going to be even a longer tail. So you can see, the tail is quite long till here, right? So this is even more positive skew, Arvind, to your point, right? Then we can do the bivariate plots just like what we have done in R. So the same command, proc sgplot, data is prac, scatter. X-axis is going to be years of driving experience, y-axis is going to be the cap losses, and I can have certain amount of transparencies and so on and so forth, which are more for the cosmetic things rather than anything in terms of the actual dynamics of that. And you see that it basically mirrors the same chart that you got in R, right? So you have the same chart coming in here, and you can see the same sort of trend emerging here, right? So similarly, I can do for some other variables as well, not a big deal, and I will just run it very quickly. I'm not going to run for each of the X and Y variables, but you can see, I mean, how we are able to mimic what we did in R in SAS as well. Arvind says, should binomial be a better model? No, not necessarily, Arvind. I mean, overall the R square value is quite good. The model is a great fitment. So I think even a linear regression model is going to be a great model here, right? Now let's focus on these lines. This is where we are actually running the linear regression. The procedure for running the linear regression is proc-reg, right? Proc is a short for procedure. Reg is a short for regression. So you're running a regression model. Data is packed linear. Alpha is 0.05. So this means with the 95% confidence level. Plots is equal to all. I want to plot everything that we have. Then this is where you actually specify the model. So your model is that this is my y variable. This, then you have the equal sign like the tilde sign in R. Then you have the independent variables separated by the space. Remember, I mean, in SAS we do not use comma, we use space to separate out the independent variables, right? And what we are doing over here is basically a stepwise model. I mean, this is a very, very sophisticated model. Stepwise model is basically, you will be throwing in variables, you'll be throwing out variables at the same time with the alpha of 0.05. So if they are significant, they will be entered. If they are not significant, they will be exited. And we are looking at the, the confidence interval, the VIF, and ACOV is what we will be using for fixing the heteroscedasticity. ACOV. You can look at each of these options as I stated earlier. So for example, if I go here and type space, and if I click on ACOV, it will say displays the estimated asymptotic covariance matrix of the estimate under the hypothesis of heteroscedasticity and heteroscedasticity consistent standard errors parameter estimate, right? So you can figure out what each of these parameters are. And I want to have the output created in a file. So this is where the file is going to be saved. and this file is a temporary file because I'm using the library name work, and I want to have the predicted losses. I want to have the upper confidence and lower confidence, just like what we have done. And let me run this model. Don't worry if you don't follow SAS, because we'll be focusing more in R, but this is at least, you have the code, you can try it, and it's very, very straightforward, right? So you build your model, and it basically gives you the stepwise, how in the first step which variables entered, right, and how they were behaving over a period of time, and it will continuously give you a lot of different output, right? But over here is where the mother of all output is going to be, which is this, the final output, right? And what is there in the final output? Same way, Arvind. So, I mean, you will be doing the flooring and capping the same way. In the SAS, you use the if-else statement. The syntax was there in one of the previous videos that we talked about. So, if this is this, else this is this, right? So, you can use that to do the flooring and capping, right? If you want, I can send you that code again. Yeah. Guys, this is where you are looking at the output, right? So you can see that the WIF is under control because of the runs that we did, the entry and exit criteria, the stepwise function. And over here, we are looking at the heteroscedasticity consistent confidence limit. Over here, we are looking at heteroscedasticity consistent standard error. So basically, you have fixed both heteroscedasticity and the multicollinearity in this model right there by running that particular line of command, right? Now, some of this I'm doing, I mean, but you don't have to necessarily do that. I mean, you can actually create the deciles, for example, right? So, for example, first thing I'm doing is I'm sorting this data, which is the data that is created by the output. And I'm saying, sort by the descending predicted losses, right? So the data is going to be sorted. And because it is sorted, the new table will be, in the descending losses. I am saying if the observations are between this to this, which is basically, the 10 different equal bins that we're looking at. And you'll see that how we can do it much more easily in R tomorrow when we look at the function called entile, right? And that we'll be talking tomorrow as well, right? But in this, I'm doing it manually. And this is how, Arvind, to your point, you can do the if statement in SAS. If this is less than this, then bin is equal to this, right? Else between this. So basically, I'm creating 10 equal bins, and then I'm plotting those bins to see how the performance of those bins look after I built the model based on the predicted percentages of default. And there you go, right? So I have created 10 equal bins. Right, and the cap losses, and you can see it's basically rank ordering, and by design it should rank order because I have created those bins. And you can see for each of these 10 bins, the number of observations sitting in each of these 10 bins are 1529, which is nothing but 152900 observation, if you remember earlier, divided by 10, because I'm creating 10 equal bins, so I will have 15290 over the total number of observation, 15,000, and then I'm actually removing the 0, and that becomes 1529 in each of this, right? And it gives you the mean of the predicted losses, standard deviation, minimum and maximum, and it basically plots it over here, right? And this is how you will be doing that. How does this help in understanding the data? So it's not really necessarily helping you to understand the data directly in the bins, but the bins are more useful when you want to execute a strategy based on this, right, Arvind? So for example, if you are part of bin 1, you have very high probability of default versus if you're part of bin 10 where the probability of losses will be very low, right? So basically, instead of looking at the actual predicted number, we can look at the bins and we can have a treatment based on the bins. So that is the thought process behind that. Yeah. Okay, guys. So this is about the SAS, and this entire code I have saved in the learners folder. You can give it a go. You can try what really happens. Some of you don't even have SAS installed, so don't worry if you don't have cannot follow. But at least you will try the R code that we discussed, and you will try to figure out everything that happens there. And if you have any questions, you will come back to me with the questions by tomorrow. Does it sound like the plan? Yes, our code is also available at the learner site, Nausea. So I will just point you guys to that location again, right? So if you go here, R code is available, right? So this one is the R code. You have the raw data, you have the cars file as well, and then you have the SAS data. So try everything if you want to, but at least at a not bare minimum, at least at a bare minimum, you should try the R code and make sure that you are 100% comfortable with that, right? Because we spent a lot of time talking each line, in great detail. So make sure that you're 100% comfortable by the time you come back. And tomorrow, what we'll be doing is tomorrow we'll be talking about two very, very important topics. And the first topic that we'll be talking about tomorrow is logistic regression. And I will put some material, I think before I go to bed today in the learner portal. So give it a try, logistic regression. And then second one is the decision trees, depending on how much time we have left from the logistic, right? So decision tree will be the second topic that we'll be trying to cover, both of them tomorrow. Yeah. Okay. Any questions, comments before we break the session for today from anyone? Are we good? Does it make sense? Are you getting some good hang of some cool analytical techniques? Yes, Hari, I will talk about how the files are exported as well. So Dimple says it was a tough session for me today. Please make the video available at the earliest. Please. I will do that, Dimple. Yeah, definitely. So, I think, guys, you have to take it slow. So watch the videos, make sure you're comfortable. So in case if you have anything that doesn't make sense to you, write to me. Better you come to the class tomorrow 15 minutes earlier and we'll discuss that. Gaurav says, can you please tell us the libraries that need to be installed before a session? So Gaurav, I will put the code also in the learner page, so you can actually make sure that whatever libraries are referred in that code, you have installed them before you come, right? Will it work? Cool. Okay. Any other thoughts, questions from anyone? So, but one thing for sure, we will not be doing anything further on in the SAS, because SAS we have touched upon the basics and we have showed how to do things in multiple ways. From moving on, from the next lecture onwards, moving on, we'll be doing mostly in R, and you'll be, sort of like going through some of the key concepts like the recommendation engine, the logistic regression, the decision tree, so on and so forth. Right? So it's all coming your way. It's going to be a little bit intense as well, but hopefully you'll be able to enjoy that, right? Cool, guys. If no further questions, let me give you back 45 minutes or 40 minutes of time today, so that you can enjoy with your family, friends, and do some other things. Be on time tomorrow, and make sure that you do the pre-read as well, right? So Gaurav says, good night. It was an awesome session. Thank you, Gaurav, so much. Will we cover multiple samples out of a population to compare which model is statistically significant, and are we dependent or not? Arvind is asking. You can do that, Arvind, but the key insight there is that you just do a random sampling to begin with, and then you build your model, on that random sample. Ankit says, sir, I may not turn up tomorrow. No problem, Arvind. Sorry, Ankit. Watch the video. Make sure that you're comfortable with that, right? Cool. So thank you, everyone. Let me say good night, good morning, good afternoon to everyone. Thank you so much for your time and patience. And I will see you tomorrow, all of you, whoever can make it. Good night. Thanks.